So, so Rn, look at Rn. We will not look at general vector spaces, but look at Rn. Okay? So, we look at Rn as a vector space. Okay. So, what do I mean? I mean that you have Rn, then you have this addition operation, and of course you have a scalar multiplication. Okay. So, this dot, right? This dot is referring to just taking a scalar and taking a vector and returning this. Yeah, just the simplest thing. So that is what this is. This is not the dot product. So this is in general what is called a vector space, but we will just look at this. Okay? So what are we going to do? We are going to learn about this thing. We are going to view this as a, so view this V as a vector space, number one. And the reason why I'm doing like this, so we can use some of the things we have done in matrices. Okay, some of the things we've done in matrices, we can apply them to learn about these things. So that's why we are taking this coordinate approach. So we will define dimension, and also we will define this. Yeah, but then for this we will need. Okay, no problem. We will define the linear transformation. And then we'll define the dual space and its dimension. And possibly also a relation between transpose of a matrix between matrix transpose and dual. We will go slightly further. So in this, I don't know what is the first thing to do. So let us first define the, so Rn is a vector. Not working. Right. So first concept is linear independence. Linear independence. And actually, let me just define this for general vector spaces. Okay. So let me define vector space here. So V is a vector space. It's just very, very similar to Rn. And so V is a set. Okay. Vector space is just a set. And then it has an addition operation. Addition operation. Okay. And a scalar multiplication. Aryan, have you seen the formal definition of a vector space? Over, say, over a field length. So if V1,
Sir, did you call?
Yeah.
Sir, did you call me?
Yes. Have you seen the definition of a vector space?
Yes, sir.
Okay, then it is fine, right? So basically, V1 and V2
Yes,
are
yes.
elements. Then there is an addition and it's commutative with scalar multiplication. So then it's not a problem. Okay. Actually, yeah, we will need to look at arbitrary vector spaces, otherwise there's a problem. Yeah. So let me just talk about this, the linear independence in a vector space. So what is linear independence? Linear independence is a property that is associated to a subset of a vector space. So let S be a subset of vector space B. B represents vector space. Okay? Vector space over a field F. You can think of Rn over R. Okay? And S is a subset. So S is linearly independent.
So the scalars come from R.
Right. You can think of it, but I'm just doing scalars can come from any field F. Any place where you can do multiplication. Q rationals is fine. Complex numbers is fine. Integers modulo P is fine. So you can do inverse there. Yeah. So all such things are okay, but we'll just denote it as F. Yeah. So, Arnab, can you tell us what's the definition of linear independence for set S? Given a set S, when do we say that S is linearly independent? Or if you know any setup, you can say. Right? So, okay. So basically, given any, better to use like this, given any k things in S, okay, lambda 1 v1 plus lambda 2 v2, and lambda is a scalar multiplied to that vector, plus lambda k vk equal to 0 implies that, so basically never 0 unless in the present case, implies that these are all 0. Right? So you pick any finitely many vectors from S. Okay, you may have seen some more simpler definitions, but this is definition I'm saying. Okay, and this is also a common definition. I'm getting some slight allergy. Yeah. This is not my room. Anyways, so there is this k, right? So given any k vectors from S, given any k elements from S, elements or vectors, same thing. Any linear combination is 0, then basically it's a trivial linear combination. Okay. So why are we interested in this set? We are interested because we will look at can I say it without? We'll just say we'll look at a maximal linearly independent set. Maximal linearly independent set. Okay. We look at this concept. Okay. So what is a maximal linearly independent set? Anyone? So it just comes from linearly independent set. It's not a new definition. So can you give an example of a linearly independent set? No. I think what vector space should you take and what S should you take?
Can I?
So
Yes, yes.
So if we take a set, linearly independent set, and if we just eliminate one element from there, so
Uh,
that would be less number of elements in the set, and that would be also linearly independent. So
right.
when we are when we are looking into a vector space, the biggest linearly independent set, and I mean the highest number of linearly independent element there are, then the set will be called maximal linearly independent set.
Yeah, I mean the definition, what you're saying turns out to be correct, but that should not be taken as a definition because there's a problem with that. Yeah, but before that, can we give example of linear independent set?
Sir, I guess, so if we're
Basic.
looking at R2
Mm-hmm.
and we take 0, 0, comma 1 and 1, comma 0.
Right, that's a linearly independent set, right? Any other example? Arnav, do you have any examples? We just want
In
example.
R3, in R3 1 0 0 0
Right,
1
right.
0 and 0.
Any other examples? Like I understand.
Yeah, 1 0 1
Huh?
0 and 1 1.
Right. But how about this? You look at the collection of all polynomials, right? This is a vector space.
Yes. So the basis will be I. I mean, if we just consider the set A plus bi as A comma B,
Mhm.
then, it would be 0 comma I.
Right. No, these are polynomials.
Oh, sorry.
So then we can take, okay, 1 second. So the polynomial x squared and the polynomial x.
Right. These are linearly independent, right? This set will be linearly independent because actually that's the definition of polynomial, right? Or I mean, anyway, anything you want, right? So if you take cx square plus or lambda 1 x square lambda 2x, if this is equal to 0 for all, this is equal to 0 means what? This is equal to 0 means this is 0 in this, right?
It is a
And
0 polynomial itself.
right,
So
yeah. So 0 polynomial means that all coefficients must be 0. So no matter what definition you take, if you take algebra definition, then it's a definition of 0 polynomial that all coefficients should be 0. If you think of polynomials as functions, then 0 means a 0 function, and that also implies that the coefficients are 0. So both ways it's the same story. So this is the thing. Okay, so yeah. Anyways, so vector space doesn't just mean vectors. Yeah, and yeah, so I have to change the room. So, and now try to frame the definition of a maximal linearly independent set. So maximal would be, in terms of subsets. Like maybe we can talk about this more carefully today. Uh, yeah, so because a linearly independent set is a subset, so maximal should be it's a maximal subset. Means that it is not contained in any linearly independent set. That should be the definition of it. So now, can anyone tell me the proper definition? It's not based on size. Eventually, it is. That's a theorem, but usually we don't do. So maximal. So I have defined it, right? Maximal linearly
So
independent.
sir, is it,
Yeah.
so sir, is it something like if we like it's a linearly independent set, but like if we
Mhm.
take any other arbitrary like element like vector, then it becomes dependent.
Yeah, you can say
So
right.
like the biggest in that
Exactly.
sort of.
Yes, right. So basically, it is not contained in any linearly independent set,
Okay.
right? So if you add anything to it, if you add any other element to it, then it is then that new set is no longer linearly independent. It becomes linearly dependent. Okay, Arnav, is that fine?
Yes, sir.
So that is how maximal. So you have to always be careful with maximal and maximum. Right? When we say maximal, it means maximal. Right? Maximal means it's maximal with respect to set inclusion. So it's not included in any set of its kind. Means that which is maximal. Sorry, which is independent. It is not included in any set which is independent. All this will be clear if you look at theory of partially ordered sets. But yeah, we don't need to do everything for it. Right. So now can you tell, especially from the perspective Aryan said, maybe you can use that or see, why is maximal linearly independent set interesting? Yeah, think about that. Why do you define this term, maximal linearly independent set? Going. You see, given a vector space, we would like to find a subset of vectors using which we can get every vector, right? So from that angle, you can think. So actually, you will see that this maximal linearly independent set can be used to get any other vector, taking linear combination. So let's talk about this. Yes. Is it everything is fine? Is my voice okay or no?
Yes.
Yes.
All right. Yeah. So we will not reach our goal today, but it's kind of chapter 2 of art in what we are doing. But it's fine. We can do it, and we will do it in a slightly different approach, which mixture of some books. No, this is not good. Sorry. So can anybody tell me what is a generating set of a vector space? Let's talk about generating set and we'll come back to maximal linearly. So D,
Sir, I don't know, but going by the name, like, is it like a set is subset of V from which, like, you can get every other element of V using like linear combinations or something?
yes, that's that is fine, right? By using linear combination, because that's the only thing you can do, right? By using linear combinations is the only thing you can do in a vector space, because when you add two vectors, that's also a linear combination. Yeah. So generating set, let's call it S for the moment. Okay. I think this is a good notation. Generating set S. Then yeah.
And if you want it in terms of minimal or maximal, so it will be minimal
Generating
in
set.
linearly.
No,
Uh,
say it again.
Minimal generating set. Sorry, basis. I mean, basis would be
Yes, that becomes a basis. Exactly. Right. That becomes a basis. Correct. So minimal generating, so generating set is fine, and minimal generating set is fine. So we can go faster. This is fine. Now you show that maximal linearly independent set implies that it is a minimal generating set. So you should first show that it's generating set, and then you can show it's a minimal generating. Why is it a generating set? More or less obvious, right? Okay, sorry, I used S for this also. So I will not use S, I will start to use I for this. Maybe this I. Okay. So I is a maximal linearly independent set, so that it is a generating set. Yeah. So you take any vector, so you take any V in V. Okay. If V is in I already, nothing to do. If V is not in I, then what do you do? This implies that V union I is not independent. This implies that there is some subset whose linear combination is zero, right? This implies that there is not linearly independent. This implies that there is V1 Vk in this thing such that lambda 1 V1 lambda k is equal to 0, and all of them are not 0. Some of these three might be 0, but all of them are not 0. So far, I've just written the definition, nothing else. Now I want you to conclude, somehow bring V in the picture and show that V is a linear combination of the other things. That is what you want to show here.
So we can just like rearrange the equation to like get V, right?
Okay. First, you have to show then that V is there in one of the VIs. One of the VIs is V. You have to show that. Oh,
So, but if it was not if that were not the case,
yeah.
then it would like be linearly independent, right? Because we are adding V, and that's why we're getting the zero. That's why we're getting the dependence.
Correct. That is it. Yeah. So if V, I'll just say it. I'll just say the same thing again. So if V is not one of the VIs, okay. If V is not one of the VIs, then these VIs are in I, capital I, right? This V1 to Vk is in capital I. But then if they are in capital I, then this is not possible. We have already said that's the definition of linear, right? So V is there, and so V is the first one. Okay. So then what do you do? So then the first one is, and this lambda 1 is not equal to 0, right? Because
Yes,
that's
again,
what it
and yes, sir, same argument.
correct. Then what do you do?
So then we rearrange, like we can put lambda 1 V as minus of lambda 2 V2 and so on.
Mhm. Okay, then
And then we multiply both sides by inverse of lambda.
right. And this is the first place where we are using field structure. Right? This is the first time we
Yes,
are using
yes,
field structure.
inverse and so.
Right, all those. Especially the multiplicative inverse. Additive inverse is always there, and even in rings it is there. Groups it is there, but the multiplicative inverse is necessary at this point. Okay. So anyways, all this you can do. Yeah. Arnab, it's okay. This is good.
Yes, sir.
Right. This is probably easy. Now you try to show that this is the homework is that you try to show that In fact, the other direction is also. So these two are the same concepts. All right. But this is the homework. You have to do it. You don't know. So again, let's remind ourselves why we are doing these things. We are doing these things to establish what it means to be dimension of a vector space properly. We want to establish. And once you understand dimension and these things, then it's it. You can look at MMath papers. Yeah? You can look at usually the first 7, 8 to 10 questions in MCQs are linear algebra, and now you have access to understanding those questions. I'm not guaranteeing you can answer them right now, but that you cannot guarantee even 1 day before the exam. I cannot guarantee for myself also, but that's not the point. You should be able to understand. And similarly, I mean, MMath is a very standard exam, so it means the jam or any understand the questions. So I think let us stop here with this. Let's not move forward, and then it becomes a bit too much. And let you guys ask me some questions about what we have done today. Anything which you want me to go over.
Is there anything to?
Anything which you want me to repeat from what I have done today.
No, it's okay.
So, second question is anything I can help you with to help you move forward in art problems, solving problems from art in. I can open the book right now and tell you some, if you want some hints or something, because I want you to make progress in that. Any problem that you are stuck in and you want me to.
1 minute.
Because the dual space theory is obviously a bit still a bit far, but he covered it, and Arnav has already written most.
You told me that you will tell the 3.4 answer.
3.4. Okay, so maybe let's treat it as some further hints. Let me just put it back. I'll not tell the whole solution. Yeah. So from a matrix perspective, it's a bit it's a tricky question, slightly tricky question, but let's do it. Yeah. Right. So let A be a M by N matrix. Aryan, have you done that question? Have done this one? How much can a matrix be simplified?
So that day after we like shortly discussed it, I did try it.
Okay, okay.
You did say that we can, if it's n are non-zero, but I did a few examples, but I don't know how to prove the general case.
Okay, okay, right. So let's do it. Yeah, no. First, it's not difficult. It's not difficult. So it's just that I have to think the way to say it. First, if I want to simplify one operation or okay, yeah. So you know that using row operations, how much you can simplify, right? Using row operations, we can write A in this form. Let's say that it is M by N. Okay. Then you can write it in this way, which is called a row reduced echelon form. If you don't know how to do this, then consult some books, discuss this later. And this is like an example. I can give you the general definition. If I myself am writing, we cannot comment on this. So the stars means that we cannot comment on those. It may be 0. This one also we cannot. Yeah. So do you agree that any matrix can be reduced in this way? I will define this way if you want. But
Yes, yes, agree.
agree, right? Yeah. Maybe let me make it slightly more general. Okay. So this is by Gaussian elimination, right? So again, now what is the definition of this? If you roughly, so Gaussian, so you should try to do this. Okay, Gaussian elimination of a system of equations, which we talked last time. You can do this. So you understand, right? So what is this? This is like every row has a 1, right? If it's a non-zero row, then its first non-zero. So every non-zero row has its first non-zero entry is a 1. Okay, first non-zero entry means scanning from the left. That's the situation. And then when the entry is 1, then that corresponding columns, all the entries below are 0. You can see, you can do those things with row reduction. The entries above, I don't think, no, sorry. Yeah. As I said, then I can see better. Yeah, obviously, the entries above you can also make 0, right? In those columns. Yeah. So the columns where the columns corresponding to the first non-zero entries of some row are entirely 0 except for that entry. Right? This much you can do with only row operations. Okay. This is called row reduced echelon form. Please try to write a proof of this or try to read this. Artin or Hoffman and Kunz. Now the question comes, what can you do if you have column operations? And by the way, in the end, we may have some 0 rows. There are more terminology, I'm avoiding them.
In column operations, we can do the same also.
Yeah. Then
I mean, we can get the same form of that matrix.
same form means what? You can make it simpler because column operations would mean that how to say? Then basically these become your so you are doing row operations, right? So now if you do column operations, then you are working on the columns, right? Then you can do the things on the columns and
If you
right.
work on the column, get the most simplest form as the transpose of this matrix.
That won't be the most simplest. You can simplify it further. Yeah. So then let me talk like this. Okay, let me say like this. Okay. Now when you come to column operations, then you think. When you come to column operations, then you think of them as row operations on the transpose matrix. Okay. So this becomes your row 1. Is that fine? This becomes your row 2. This becomes your, now these are the rows and you're doing row operations. That is what doing column operations means, right? You agree? Right? Because column operations will act on the columns, right? But yeah, if you call the columns rows, then it's like doing row operations. If you think of all these things as your rows and you look at the matrix like this, right? Then now tell me, if you do row operation, now forget now column operations word we don't need to use, right? Now if you do row operations on this matrix, then what can you do? Just look at it like this. If you do row operations, then what can you do? Obviously, every non-zero row has a first every non-zero row, the first non-zero entry is a 1, and that becomes a topmost entry. You can use it to make these things 0. Agree? Yeah? Take that row and multiply it with. Okay. Okay. Aryan, is that okay?
Yes, sir.
Right? And now you understand what I'm doing. Similarly, make this 0. So boom, right? So it only has ones. Only has ones.
So,
And mhm.
so whatever we did to the original matrix, we're doing on the transpose.
Exactly. If you're thinking of the columns as the rows and doing row operations. Right. Okay. And then, so this you can always do. So you understand that you can always get rid of all the stars. So now, yeah, less than a minute is left. I will not go forward after that. So you understand, right? Yeah. Now you have to just shuffle the columns, right? Now you have to just shuffle the columns and then you see. It's already simplest, but still just to. Now if you shuffle the columns, then you can put all these ones on the diagonal. You can shuffle the rows, you can shuffle the columns in this case. So then you see you have 1, 0, 0, 0. The third column you can bring forward and then it becomes like this. Maybe one more 0 is there. And similarly, you see, this is a good thing, right? So it's kind of like a block of zero. This is a block of identity matrix and the rest are 0. That's the simplest form. Okay. And that block size is called the rank of. Is also the dimension of the vector space. We will talk about this. We are stopping here. Good. We can't waste.
Yes, sir.